instructions, okay? If you go to that website, it says click on the graphing area to add 10 points. If you get more than 10, it's not a big deal. Go to the graphing area, 10 points, and try to get an R value of 0.5. Close to 0.5, all right? Okay, now that we're back here, now it says for each of the following. So on A, it says if a point is added on the far right side of the graph on the horizontal gray line, so add a point on the far right side on the horizontal gray line, and we're going to look at what happened to our slope. Did our slope increase or decrease? How do you know if it decreased? It gets more horizontal, right? Your blue line will get more horizontal. Did it get more horizontal or did it get more vertical? Horizontal. So my slope decreased. I'm just going to draw a down arrow. Okay? What did the y-intercept do? It actually is going to go opposite. Whatever slope does, the y-intercept does opposite. So like, you remember the seesaw on the playground? If your slope goes down, the y-intercept has to go up, and vice versa. They go opposite. What happened to your correlation value? Did it go down? Yep. All right. B, if a point is added on the far left side this time on the graph of the horizontal line for the mean, add it on there and see what changes happen.
Do you want us to keep the dot?
No, you can leave the other dot there. It's fine. You just add a new dot. Okay? So what happens if you add a point on the far left side? They go down again? Yep. Slope went down, which means my y-intercept did what? Went up. And correlation? Did the R value go up or down? Down. Okay. So if you notice, we're adding a bunch of outliers, aren't we? So we're getting a little more sophisticated in what do outliers do to R and stuff, okay? Now, if a point is added below the regression line, the blue line, but it's on the vertical line that represents the mean of x. So on the vertical gray line, but below the blue line, add a point. See what happened. What happened to my slope? Did the slope change at all? Nope. The slope stayed the same. But did my y-intercept go up? It went down. Did the correlation go up or down or stay the same?
It went down.
It went down. It's still an outlier, right? It went down. It should go down. All right, look at D. If we add a point now that's above the regression line on the vertical line, what happened to my slope? Did the slope change?
No.
Nope. Slope stays the same. But did my y-intercept change? Yeah, it went down. What about correlation? Down. Now, let's kind of back up and think about this for a second, okay? The first two changes we made were along the horizontal line that represents what, the average of my y's? No, is that right? I think I said that backwards. These first two, so it changed my slope, it changed my y-intercept, and the correlation. Everything changed, didn't it? So what that's doing is tilting the line. I'm going to draw myself a little teeter-totter, right? You put down and it goes, that part goes down, this part goes up. Those tilt the line. So we add a point. It's like a horizontal outlier, right? A horizontal outlier will tilt the line. It messes with your slope, messes with y-intercept, and it messes with correlation, okay? But a vertical outlier, those are the other two that we did here, vertical outliers, it didn't mess with everything, did it? It kept my slope, but it did move my y-intercept. So really what it's doing is just transforming that graph, moving it down or moving it up, shifting, a vertical shift, okay? A vertical shift. But it does change correlation, right? Now, so let's think, why is it changing correlation every single time? On all of these, why did correlation go down?
Because they're all outliers.
Yep, R went down on everything because all are outliers. Outside the pattern, right? Yeah.
On part E, did you mean to put like the y-intercept goes up?
Oh, did it go up? I think it did actually on that one, didn't it? Yes, I did. Thank you for catching that. Yes. Okay, so then the question becomes, okay, looking at outliers, which outliers have the greatest impact on the regression line, the vertical ones or the horizontal ones? Horizontals. Does everybody agree with that? Horizontal, because it's messing with slope, y-intercept, and r. It's messing with all parts, right? So this is what we're talking about today, is the influential points. What kind of outliers really mess with our lines? Okay, we already did a really brief thing of, okay, some outliers help. But let's get more specific. So on the next page, we're going to summarize this. So here's some vocab, some we've already seen. Outliers, we already know outliers, right? It's a value that's outside the pattern. That's going to be an influential point. So if it's outside the pattern, that is going to have a high residual, isn't it? Now that you know residual, that distance from the predicted line is going to be much higher. Then we have, here's a new term for you, high leverage. Think about your seesaw on the playground. Which ones tilt the line? Well, those were the horizontal outliers, right? Very large or very small x values. Those are high leverage points. And then we have influential points. These are points that cause big changes in slope, y-intercept, or r. So if one of those three is changing significantly, it's just considered an influential point. Maybe it's considered changing one or maybe all of them. Just depends on the graph, okay? So that's some vocabulary you may see. So let's look at this. Outliers and the regression line. We said this, horizontal outliers will tilt the line like a seesaw. Okay? Depending on where that outlier is, it's going to tilt the line. Think like a seesaw on the playground. And what did we observe that the vertical outliers do?
Shifted the line up or down.
Good, yes. Shift it up or down. Up and down. That's all. So it may change your y-intercept, but it's not going to mess with my slope. So a good regression line has a low S. Remember S, we talked about that yesterday, is the standard deviation of the residuals. So it's a really well-fitting line, low residuals, right? And a very high R squared, meaning whatever X is a really good predictor of Y. Closer to 1 or 100% we are, the better predictor it is, okay? Then there's this little extra thing that's called regression to the mean. So this is actually on, these formulas are on your formula chart. You don't ever have to memorize them. If you have trouble locating them, I'll help you find them. They're on the front of the page at the top. But sometimes we are only given the mean of the y's and the mean of the x's. Because with any regression line that's calculated, the average x and the average y, that coordinate pair is part of the line every single time. Okay? It's like the fulcrum on the seesaw, right? That's the pivot point, basically. So every line has an x bar and a y bar. Now we can use that to find slope, and we can use it to find y-intercept. In order to do so, they have to provide these values. So B is my slope, according to this. And you have to have a correlation coefficient. You have to have the standard deviation of your y's and standard deviation of your x's. And you just plug and chug here. You just put them in the formula, crank it out your slope, all right? Then you can use that slope, use the x bar they gave you and the y bar they gave you to find A. A is my y-intercept here, right? So if I was solving for A here, it would be what? Y bar minus B times x bar. You don't have to rearrange it, but I just want you to see that that's how you would find A, that y-intercept. Use the equations you're given and the values you're given. So these are like plug and chugs. Again, they're on your formula sheet, nothing you have to memorize. You just got to remember that they're there. Okay? So let's look at these, this practice question here. Probably heard the saying that practice makes perfect, but does practice also help you complete a task faster? A study was conducted to find out. A random sample of 15 high school students were taught how to solve a Rubik's Cube. They were randomly assigned a number of times to practice the new skill. After they completed their assigned number of practices, they were timed during solving the Rubik's Cube. Here's a scatter plot of the results along with the regression line. Describe the influence the student who was assigned to practice following the steps to solve a Rubik's Cube 14 times had on the regression equation. Okay, where is he? Well, that's this dude up here, right?
Yeah.
What did that person do to the slope in our y-intercept?
Shifted the y-intercept up.
Let's think about this for a second. What did it do to my slope? What did it do to my y-intercept?
I feel like I changed the slope to make it
Once that point was added, that line had to tilt up a little bit, didn't it? To grab it, to reflect it a little bit. So what did that do to my slope? It increased it slightly, right?
Yeah, when
I guess it's negative.
Let me think here.
Negative slope.
Since it's because it's negative, it's an increase, right?
Oh.
It's bizarre because it's negative. So since it's negative, it actually increased my slope. Okay? So it's less negative, that's all it's saying. It's less negative, right? Okay, so if that's what happened, if my slope increased, what happened to my y-intercept? It decreased, yep. Yep. Because, think about it, it's a high horizontal outlier, right? So we know it's going to affect both. All right, then B says, describe the influence the student who was assigned to practice this same dude here. What influence did he have on our standard deviation of the residuals and our R squared? So what influence does he have on S? Definitely increase it, because think about the residual it's adding to that calculation. That's a very large residual, isn't it? Remember, standard deviation is what is the typical residual, right? It's making it much larger than it had to be. Okay, so it's increasing. And then let's think R squared. If you're not sure, think about R. What is that point doing to R? Decreasing it. So it'd have to decrease R squared too, right? Okay, now the line is not as great a fit because we have this random outlier. Number 3 here is just practice using those formulas. So we gotta kind of have to deconstruct what it says. The mean and the standard deviation of the number of practices, our x bar is 8. The standard deviation of the x values is 4.47. The average time is 7.71 minutes, and the standard deviation of the times is 1.20. And then they give me an R value of negative 0.793. So using those values and the equations that are given, remember we know that B is equal to R times s of y over s of x. So we're going to just plug and chug here. 0.9793. And I get negative 0.213. That is the slope of my line. And then to find A, we said we're going to do what? Y bar, 7.71 minus our slope times X bar, which was 8. So when I do all that, I get 9.414. So then my regression equation, the predicted time would then be 9.414 minus 0.213 number of practices. Okay, can y'all read that? This whole formula thing is one of those things that they may or may not ask. You just never know. Sometimes they throw it into multiple choice, and you just got to remember you have an equation to do it with. Okay? So that's all there is to that. It's called regression to the mean because it's the mean of the x and the means of the y's. Everybody see it okay?